Our next speaker is Joel Yee from Carnegie Mellon University, where he works with Leila Webe. He's a computational neuroscientist and did his practicum at Lawrence Berkeley National Laboratory. And today he's going to tell us about towards foundation models for brain-computer interfaces.
Great. OK, thank you for the intro. Yes, so you've heard a bit about foundation models so far, and so I will talk mostly about brain-computer interfaces. Let's talk about what that is. Brain-computer interfaces, the types of devices or systems that I'm interested in, are sort of rehabilitative devices. They are designed currently for people who suffer from spinal cord injury and are paralyzed or have neurodegenerative diseases, and in some way or form have lost access to their native sensory motor capabilities. So we have various demonstrations here of BCI systems that have been shown in academic settings and also sort of like industry demos for restoring speech, for like controlling robot arms with basic functions. There's a person who has a basic sense of sight restored. And the sort of maturation of BCI technologies has reached a point such that there are like well-funded BCI companies that are trying to scale up the production of these devices for people to actually operate these BCIs independently without sort of like research oversight and actually restore a sort of basic sense of independence for these people who are otherwise very limited in what they can do. How do these devices actually work? So the specific class of BCIs that have the sort of highest performance to date, generally speaking, are implanted BCIs, which sort of bypass your skull, the outer layers of the brain, to directly interact by using like really fine electrodes and record directly from individual neurons. So if you place your electrodes, or like a whole bunch of them, really close to the right areas of the brain, you can get really high signal quality to tell you actually when a person's trying to move their hand left, you see some neurons fire, and trying to move the hand right, some neurons fire. And so that's an oversimplification, but for example, the raw data I'm showing coming off of these devices would look something like this, where you see sort of a population or a group of neurons getting recorded by these different electrodes, and each of these little black marks is when a neuron fires or activates really strongly, right? And so this is a spontaneous activity, but over time, you see this rich like pattern of firing. And our goal as modelers or BCI builders is essentially to decode these and relate those to the intention of the user, right? Whether they're trying to write some characters or speak or whatever it is. Because these neurons are really directly related if we implanted our devices correctly, the classic models to understand sort of individual neurons and also populations of neurons will be linear. They can be really simple. So like I said earlier, right, you would canonically describe a neuron with a tuning curve and say, OK, this is a leftward tuned neuron. I'm moving my hand left, and it fires really strongly. And as your hand direction goes farther away from pure left, it fires less strongly. And this is wonderful. But of course, in recent times, many people have been attempting for a nicer or more off-the-shelf method, because who wants to think about all these individual models? Instead, there's a sort of ideal that we strive towards when we're building big foundation models for BCIs, where instead of thinking about a custom small linear model for any given person that maybe breaks after 30 minutes, we want our deep network BCI to constantly work for any person, anytime, hopefully, regardless of what they're trying to do, just work, man, right? And I spent a lot of my PhD basically trying to take like baby steps towards this goal. And the kind of narrative I've thought that any sort of natural science domain should take, in addition to sort of more specifically like my work, is you kind of carve out tiny pieces of your domain, right? And start with an individual data set, show that your deep network actually is competent, compares to a baseline, so you don't have like a sort of paper calling you out like 10 months down the line, and say, it's comparable, and you take pairs of related data sets. There's transfer learning. There's structural similarity between the different data sets in your domain, whatever that similarity may be for your domain. And eventually, for everything under the sun, in your tiny little area of science, you have a foundation model, because you can train on all those little related data sets, and then you hopefully have some coverage and support. So what are the relationships for BCI in neuroscience? I have these little icons in here to indicate sort of like the first things you come across when you sort of set up a sort of neuroscience experiment or BCI experiment. Like I mentioned, there are going to be differences across data sets you collect at different points in time, sort of like batch effects if you run experimental sessions. And of course, if your device is implanted in different people or the person is trying to do different things, then your data is going to look different. And the reason there are citations under each of these icons is because the sort of dissimilarity has been quantified, right? So if you just have some really basic measure of like, well, how correlated is your data from day to day, it is not correlated, right? Like a 1 day out, suddenly you're like very dissimilar from the data that you recorded on the same day. That's unfortunate, but these are fairly recent citations. So the reason they're recent is because there's been more work to try to like understand and linearly align the data from day to day. And in each of these cases, there's already been demonstrations that if you do some basic transformation of your data, the data will actually look fairly similar from day to day. You can do a sort of CCA or canonical correlation analysis and say, OK, the data from across different days through a basic alignment procedure is almost as similar to the data as I collect on the same day. And this is a kind of sufficiency condition to basically go ahead and say, OK, I will try to build a deep learning network, because if a linear network can do it, well, hopefully then we can build deep learning. And the question is, does deep learning scale differently with these different types of data, which are all kind of similar, right? So this is a kind of like scaling question, like what types of data are most productive to sort of train my large deep network with? And I think neuroscience is like fairly accessible to the general sort of audience. And what we see here is like the only task we're basically trying to try to consider in this whole slide deck is we're going to take some neural data. The monkey is simultaneously performing a task, or a person is performing a task. They're moving their arm around, and we have some simultaneously recorded behavior, just the camera tracking their finger movements, and say, can we predict what the monkey is doing based on sort of what the neural activity shows? It's just a decoding task. And so if we have a small amount of this sort of like simultaneously recorded neural data and behavior, and we build a basic small deep network, and we get some small, modest performance at predicting the hand velocity. And we get uplift if we pre-train on some type of other related data sets. This is sort of expected, but just to describe the lines here, if we have a different monkey doing the same exact task, and we do some pre-training, and we have like 7 hours of that data, we get uplift to like 0.5 r squared. That's the orange line. And if we have cross-task data, which is different monkeys doing different other related arm movements, then it seems to follow a similar trend. It keeps going up and to the right, which is good. If we had 7 million hours, maybe we get 1.5 r squared. But there are different types of data. And as I mentioned, you would expect that the same monkey on a different day kind of has like more similar data, kind of based on vibes here. But cross-session data is kind of the most expensive data for like a BCI user, right? You don't want your BCI user necessarily to say like, OK, well, if I sit there for 7 hours, my device is going to work great. We kind of see here there's a fortunate result where cross-task data is only maybe an order or magnitude slower than cross-session data, and we can collect a lot of that because other people doing work is free to me. I kind of went out with this result and begged a bunch of experimental collaborators, because there aren't a lot of large neuroscience data sets, a lot of natural sciences like that. And we got around 2,000 hours of data, which is like the largest at the time, of sort of like paired neural activity and behavior, which are just these low-dimensional sort of like time series traces, and put it into sort of a humble 350 million parameter transformer. This is like kind of the starting point to say like maybe I have a foundation model. And the question, and I should also mention like there aren't a ton of HPC details in this slide deck, but I should mention that like this type of work would not be possible like on my university cluster. It used quite a lot of GPU hours, all sort of sponsored by the fellowship, so thank you very much, CSGF and NERSC and Perlmutter, in order to train this model. But once we trained this model, right, and we spent a ton of effort, gathering and curating and like looking at a ton of data and training the model and spending a lot of money. And so we should proportionally scale up evaluation. This is kind of the right thing to do. And the main question, scientific question, is not to say like, I beat some other person's model. It's to say like, what actual downstream impact are we going to have? And the way I think about this is through this sort of schematic, which is just to say like, there are different effects or impacts of pre-training as you have varying amounts of downstream data. This is kind of a basic concept. If you have like no downstream data, pre-training should be very helpful. If I have like one example, right, that's when pre-training should be the best. If I have infinite downstream data or like 500 hours, maybe pre-training doesn't matter at all. So we have the schematic on the left. We have an example downstream task on the right where a person's trying to like move 2 joysticks in their mind. And we have hypothetical pre-training curves, or like actual pre-training curves. On the x-axis here, like 40 minutes is going to be like our full downstream data set. 10% means like 4 minutes of calibration data. And we see our from scratch model improves as we have more of this like downstream setting. And as we pre-train, although the lines are quite faint, hopefully the points are clear, like it's just sort of uniform uplift. So this is sort of a good outcome that we see. I would say that means we're in the sort of like square-like pre-training is useful part of this schematic. And we were encouraged by this result, and we moved on to the next task, and we got like kind of like much more muddy results. This self-paced reach task is kind of like the monkey example I saw earlier. On the x-axis, you'll notice here now we're at 12 hours, so even the 10% line is kind of like farther right than the full 40 minutes we were considering in the previous example. But like this, in this task, or this time assignment, or this monkey, there's like a lot of variables to try to think about. So it's a bit hard to really tell like what exactly is causing the difference. But clearly, we're in the pre-training is unproductive sort of regime. So given this kind of like mixed situation, and you look at a few more and it's still mixed, we try to make sense of all of this by essentially just like scaling up evaluation on a few more curated data sets, which all individually have sort of like good quality control. And we get this overall trend from which we draw a conclusion. We see, as expected, right, orange line is our pre-trained curve. It is uniformly above our sort of classical baseline, black. And we have our from scratch model, which starts below the classical baseline. And there's a convergence point on this plot, which is kind of like the singular most important result, that pre-training is useful and provides uplift over sort of from scratch models up to 90 minutes of downstream data. And so for context, like, how good is 90 minutes? That's like not that good. 90 minutes is maybe a person in an experimental research setting, like, or a monkey doing like maybe like a week's worth of work. Which is like, for a person with a chronically implanted BCI, right, you got brain surgery, so you will be using your device, and you will use it for more than 90 minutes very quickly. So this is not good. And this sort of like kind of modest result exists sort of despite sort of satisfying our sort of general deep learning narrative, which is like you train your model on bigger data and you put it in bigger models and aggregate performance goes up. This is just being driven by the extremely low data regime that we're talking about, like 10 minutes of calibration. And this is sort of the setting I think a lot of like machine learning for brain foundation models might operate in, because that's sort of where you traditionally have neuroscience experiments. You have like 10 minutes of data and you run some analysis. OK, so despite this kind of modest result, I want to say overall we say like with this particular setup, with a very sort of vanilla sort of computational architecture and approach and methods and all of that, we have modest return on interest. And obviously there's a lot more work to do to say like, well, maybe it's the method's fault, maybe it's the data's fault. All of that TBD. The takeaway though is there is going to be a lot more neuroscience data collected in the coming years. A lot of BCI companies are well-funded and going to try to implant a lot of people, and they will be chronic, and 2,000 hours has already been crossed very trivially in these sort of more chronic settings. And they're going to want foundation models because there's a lot of like sort of overlapping personas in the two spaces. And even academic ventures are going to say like, wow, we have data from across the brain, and wouldn't it be great if we could just understand the brain if we gave it to an AI model to tell us the truth. This is going to be an expensive effort, right? And I think the main takeaway from all of my work is just for the field, I wish to put a bit more care into the compute we spend and designing the evaluations to make sure we're actually like making progress overall. So that's it. That's all I have. My advisors are here, Rob and Layla. My practicum advisor also helped out on this project, Christopher, funding and compute and research groups. Thank you.